Before you start this tutorial, please make sure you have the accompanying worksheet, a calculator, and a writing utensil so you can best learn from this. Okay, on this slide we have a very big word and it looks very scary. It's pronounced stoichiometry. I don't particularly like to use it all that much, especially if students don't really know what it means, but to break it down, it literally means element. Stoichio is element in Greek, so it means element, and then metry, you can almost think of it as a process. Anything when you add something, metry at the end of it, geometry, something like that. It's always talking about the process of how you do these things, and so this is kind of like the process in dealing with elements. But in this case, it's actually dealing with the quantitative relationship between substances and a reaction. So let me break that down. So quantitative, which of course means amount. So we're dealing with the amount. Then I also said relationship. So it's one thing is going to be dependent on another, and the amounts that we're dealing with is going to be dependent on one thing or another. And then the other thing I said were substances in a reaction. So these are all going to be reaction based, and that's what we've been covering before, is the different types of reactions, how to balance reactions. So we're going to be kind of putting all of this together. Okay, now again, all that's kind of complicated. That's why I really just kind of like to call it cookbook chemistry, because most students, even if you don't cook a lot, you've probably done at least a basic recipe. One that happens in my house a lot are brownies, and kind of one of the basic recipes that we use for that always has 2 eggs, and it usually has 2 cups of flour, 1 cup of sugar, and 1/2 cup of butter. Now, of course, it has cocoa and baking powder and all those things too, but I'm not going to include that for right now. Okay, so that's the basic recipe. So if we just need to do a pan of brownies, then we stick that way. But what happens if I go to the fridge and there's only 1 egg? Well, does that mean we can't make the brownies at all? Well, not necessarily, because we can adjust our recipe. If I only had 1 egg, then how much flour would I need for 1 egg? Yeah, 1 cup. And of course then we would have to reduce our 1 cup of sugar to 1/2 cup, and our 1/2 cup of butter to 1/4 cup, right? So we're essentially just halving the recipe. All right, but we can do this in another way. Let's say I have a party, and so I need to make double the amount of brownies. If that's the case, then I'm going to need 2 times of everything. So how many eggs would I need? 4, good. How many cups of flour would I need? 4. 2 cups of sugar, and 1 cup of butter. So as you can see, all of these are just a ratio based on our original recipe. And so our 2 to 2 to 1 to 1/2 is our original recipe. And then we can just base it off of that. Alright, cookbook chemistry, or stoichiometry, is really, really similar to that. So let's actually look at how this applies to a reaction. Okay, on your sheet, you should have this in front of you. And this is a reaction that you're quite familiar with. We have our 2 reactants, our 2 products. Remember, our arrow means to form. So let's actually look at what our reactants were. CH4 is commonly known as methane. O2 is, of course, oxygen. 2, because it's part of the H-NO7, has to be diatomic. CO2. Okay, got 2 oxygens and a carbon. Oh, that's right, this is named carbon dioxide. And then we have, of course, water. Okay, so what type, my stylus isn't working very well this morning, sorry. Okay, what type of reaction is this? Do you guys remember? The one that always has carbon dioxide and water? Yeah, it's combustion. And of course, if it's a combustion reaction, then that means it's also the other thing that we're getting carbon dioxide and water, but we're also getting some sort of energy out from it. That's the type thing. Combustion reactions always have that. But let's actually start looking at the models that I have here. So under methane, you have an actual methane molecule, which is 1 carbon and 4 hydrogens covalently bonded. Our oxygen, we have O2, but of course we have, but if you count them, we have 2 of them. 1, 2, so a total of 3, 4. How about our hydrogens over here? 1, 2, 3, and 4. Now, because we follow the law of conservation of matter, that means what can we expect on the other side? How many oxygens? 1, 2, 3, and 4. How many hydrogens? 1, 2, 3, and 4, and then we have our 1 carbon. So again, we have the same number of atoms on each side of the equation. They're just rearranged. Now, the actual stoichiometry that comes into this, the thing that we are now concerned with, is actually how many of each molecule do we have. And when we have a balanced chemical reaction, then that means the coefficients, I'm going to change my color here real quickly. The coefficients that we have in the front tell us how many we have of each substance. So in this case, that means we have 1 molecule of methane for every 2 molecules of oxygen, and that forms 1 molecule of carbon dioxide for every 2 molecules of water, which we can see down here. 1, 2, 1, 2. Now that's great on the molecular level, but if we go in the lab, we cannot pick out a particular number of molecules. So we have to make this go bigger. So how about we multiply everything by 6.02 times 10 to the 23rd? Because if we do that, then what are we dealing with? Yeah, we're dealing now in moles, which is something that eventually we're going to be converting over into mass. So we want to get everything into moles. So let's just assume, okay, that we've multiplied everything by 6.02 times 10 to the 23rd. So now we have 1 mole of methane for every 2 moles of oxygen to form 1 mole of carbon dioxide and 2 moles of water. So now those coefficients now mean our mole ratio. And that is our recipe, just like if it were 1 cup, 2 cups of flour, then, or sugar, it's the exact same thing. Okay, so now we have, this is our recipe. This is what's going to tell us how can we reduce it, how can we make it bigger, into what ratios. So let's say I need to double my recipe. Let's say I start with 2 moles of methane. Well, how many moles of oxygen am I going to need to completely react that so that there's no methane left over? We would need 4, right, moles of oxygen, right? Double the amount. And how much is that going to make? Now we're going to make 2 moles of carbon dioxide and 4 moles of water. We've just doubled it. Okay. All right, great. Let's say we don't have 1 mole of methane. Let's say we only have a half a mole of methane, or 0.5 moles of methane. Well, if that's the case, then we're going to have everything, or multiply by 0.5. And so we originally needed 2 moles, but if we have to multiply by 0.5, 0.5 times 2 is 1. So now we have 1 mole of methane. Now what about our carbon dioxide? How much carbon dioxide would we have? Oh, well, it's the same. If we needed 1 mole of carbon dioxide for every 1 mole of methane, it's just going to be the same that we started with of methane. And then, of course, and then we're going to need 1 mole of water. So we just multiplied everything by 0.5. Okay, now let's do let's say we have 1.5 moles of methane. How much oxygen would we have? Right, 3, because we're going to double it. How much carbon dioxide would we make? 1.5, because it's the same. How much water? 3. So stoichiometry is just all about using these relationships. Okay, now I'd like you to see what you can do with this rest of this worksheet using what you've learned so far. And I'll be around in class to help you. Okay.